Okay, welcome back to our chapter of permeability. So we have looked at how the importance of determining K. So if I can recall, we see that K is very important in determining in our ideology or what they call ideological analysis in determining the runoff by determining how much the effective runoff. Is that okay? So we say that is also very important in determining in solving problems involving pumping. Is that okay? Or seepage or heaving. Pumping is heaving. When water, if it occurs when you're excavating, and we see that the water coming out of your foundation, water splashing into your foundation. So and also it's at estimating the quantities of groundwater seepage. Determining, so it's very important now. And also stability analysis of earth structures, seepage through dams, under the dams, retaining structures, water retaining dams. Tell me how much water flow through under it. Is that okay? How much water flow through under it. Is that okay? So that is also very, very important to understand. So that you can be able to predict the thrust, the upthrust. We determine the upthrust force of water flowing under the dam. Is that okay? So flows are very important. So now we are going to look at how do we determine. So we said for the cost, if you can recall that if we said for the cost square material, we can using the Hazen, we can be able to determine using the effective size. You got 10% passing. That size is 10% of the biggest 10% particle, the smallest 10% particles, which is the largest size. That would be the effective size. Is that okay? So you can use to determine from this other empirical formula from Hazen. So from that but for others, for fine-grained soils, we can be able to determine using what we call the parameters. So parameter can be done with using two methods. Now, if the material is fine silt, sand silts, for such materials which have little cohesion, but they're not highly cohesive, we can use what we call the constant head. This is a rapid test. Is that okay? What we call the constant head. The constant head, how is it done? So you have a sample of defined area, concession area, and height. The height is between the manometers. Is that okay? Or the pressure gauges, the manometers. So you have your, now this is of L, or length L, okay? This is our L, length, is that okay? Now for these manometers, they measure the pressure between point 1, or water flows from this point to this other point. Is that okay? Now for the head fall, is that okay? When water flows from here up to here, there is a fall in what? In the head, the pressure. To measure the pressure, is that okay? The manometer is measuring the pressure, so there is a pressure fall. Now we can determine this H. So how do you do that? First of all, the sample has to be saturated. These are the polar stones or polar plates in which the sample is. Now, this sample has to be remodeled to its field density. It's better to pick and disturb sample. Is that okay? Then we put it into this in the manometer, and the area is given. The area is known. The question area of the sample is known, and the length or the distance from which the water flows from this point to this point. Is that okay? So we measure the pressure at which the water flows from this point to this other point. Now that length is L. Is that okay? Enough we can use so the head is maintained by this reservoir up. Is that okay? That this water level does not change. So a steady vertical flow of water and a constant level is maintained through the soil, and the volume of water per unit time is measured. So how do you measure the water? But after seeing that this manometer heights are constant, and also that the water level is constant here, so we can start recording. Start what? Recording the amount of water using a stop clock. So you measure Q, the volume of water, divided by the time you have used to collect. You have taken to collect that amount of what? That amount of water. Is that okay? So after recording Q, within a given time, the volume, this meter cubed, divided by time you have collected this water, then you can determine K. So from that is we say that K, V, which is equal to Q over A is equal to K times I, where I is equal to the pressure head, or the pressure difference, the pressure head, divided by the length in which that water flows, okay, between the two pressure points. Is that okay? So now we can say that V, which is equal to again Q divided by A, is equal to K into H, the pressure head, divided by L. Is that okay? Divided by, now for this is an hydraulic gradient. Is that okay? I is an hydraulic, so it is a hydraulic gradient. Hydraulic is HY R D R A U. Hydraulic gradient. The hydraulic, what do you call it? The hydraulic gradient. HYDRAULIC, the hydraulic gradient. Okay, that is our H over L. So now we can make with this. Now, because it's Q, you have timed Q, you have timed, and of course time, you determine Q. You have A of the sample perpendicular, which is perpendicular to the flow. Then you can determine make K the survey from here. So L goes up, H comes down. So now our K can be determined from this simple. So that's simple. For this now, this is for normally for coarse-grained soil. Is that okay? But for fine-grained soils, normally we use what called like clays. The flow through the sample is very slow because it's relatively for silt clays. Normally soils are very the soil for fine soil. Is that okay? The flow is very slow because normally the material is normally slightly impermeable. So it's permeable but slightly impermeable. Is that okay? Now for that we can use what called a slow method, which call what call the falling head. Is that okay? So after saturating, putting this sample and it's fully now saturated. Is that okay? We open these valves and pump out all the air. Is that okay? So the air has gone out, no more air bubbles coming out. So the water temp is high. And now for this level, now for this and this one here, this flow is contained by water is flowing through this and the flowing on, and this level is constant. Is that okay? So when you have attained such conditions that the normal air bubbles, the material is fully saturated, then you start recording water flowing from this level to this level. Is that okay? So this will be the initial height. Then you record the time. Now time t is equal to 0. Then you record the time it will, because the flow will be so slow. It will take time for water to flow from this point here to this point here. Now be t0. And that water will take the time it takes from flow to up to here to be t1. Is that okay? You record that time t1. So you record this height h1. Is that okay? So now we are going to use also the same equation of continuing of that Q is equal to V1 A1, which is equal to V2 A2. Continuity. Okay. So now for the flow through the pipe is equal. Remember the water is decreased. Now the flow is negative. Give a negative slope. Is that okay? Now for the flow through the pipe, it will be the distance covered from here up to B here, will be a change in A. Change in H, sorry. Change in H over a change in what? Change in T, which will be the velocity. Velocity is equal to distance divided by time. But that distance is negative. But this flow is negative because it's reducing from this point. Now for this negative. Is that okay? It is reducing. Is that clear? Now remember, now that will be our velocity V1. Our A will be the area of a standing pipe, which will be small a. Is that okay? Is equal to this other. Now for this equation is the flow through this other tube. Okay, the flow through the tube. What is the flow through the tube is equal to A, the area of the tube, times V. And the flow through the tube is using dashes to be K times I, which will be H H divided by the pressure difference, H divided by the length which water is moving. Because remember, it moved from here up to here. That was the H, reduction in H. Is that okay? And that will cause the flow of water from this point to this other point. Is that okay? Which will be about L. This is L. Is that okay? And be H over L. Now we can integrate now. We now see this next. Now we can arrange now for the H comes here and the T goes to the other side. Now for the flow, the summing, if you sum up the small flows, small heights from H0 to H1 is negative here. So now you can exchange this negative check, and if we move a negative, it will be from H1 to H0 is equal to AK. This is a constant into time T. And what changing is T. Now when you integrate 1 over H, the H is in H. Okay, it is in H. Now if you can substitute, remember, if you substitute in into H0 minus H1, is that okay? We'll give you this. Then from T0, from this now, if you integrate a constant, which will be 1 here, there's a constant 1 here, it will get T. Now from T minus, remember, if you integrate, you open the subtract, okay? T minus 0, which will give us the T. Now be T, is that okay? Now for this will be in H0 over H1, it is log. Now for in H0 minus, now for me, so when you remember, if you subtract logs, it's division. Is that okay? It is division. So you need to divide that, be able to determine your K, make it a subject, be able to determine that your K is equal to L, A, which is the area of the standpipe, times L, which is the length of the sample, divided by area of the sample, times T, the time it taken for that flow from this point to this other point, into in which will be the natural log of H0, the height which will fall to the height it has in reference to the height to the reservoir. Okay, in reference to the reservoir, to the bottom reservoir, or the reservoir in which water is flowing to. Is that okay? I will give that called the constant N. So for instance, if you pass through, you see this example. This example is I think it's very easy. So in a constant now, this was a constant 8. Constant 8 is very simple. It was obtained. The duration was 4 minutes. The quantity of the water was milliliters. So to change this to liters, you divide by what? Change this to liters, you divide by 1000. To change this to another, also divide by 2 meters cubed. You know that 1 meter cubed is equal to 1000 liters. Okay, so you divide it again by 1000. Now divide by 1 million, you can get meters cubed. So you can work with them. So you work now for this is for this is an example for constant, and this is an example for falling head. So you can fall through and attempt it. Okay, they just you should know how to derive this equation from first principles to get this. Then also you just need, after that, just substitute in. Is that okay? So for this one, these are equal signs. So now for we'll see that the sample, the length was what? 150. Then the diameter of the standpipe, the sample diameter was this one. Then the diameter of the standpipe was 5 millimeters. The initial head was 150. Then the final head was the initial head of water in the standpipe was this. Now the final head of water in the standpipe was, is that okay? The head above the point of 0. This is a point of zero pressure. Now for this head which pushing water to flow through into this reservoir. Is that okay? Use a head. Now this is the initial head, this is the final head. So if you get the two difference of the two using this formula here, you actually don't need the difference. So you just get H0 divided by H1. Is that okay? H0 divided by H1. H1 divided by H2. Is that okay? Then you can get this one. After getting this, then you can substitute and determine the value of what? The value of K. So, but sometimes you may not be able to do. You may do this in the experimentally in the field, what we call the field test. The field is what we call the well pumping test. Normally, these wells are normally with observation wells, spaced at a distance r, or from the radius r. Is that okay? From the center of this observation wells is to try to measure the depression of water when you pump. So there's a guy who called Duped. The Duped guy, he came up that the hydraulic gradient of water flowing through a well when you pump water out of it is given by the H over the R. Okay, is given by the H over the R. Is that okay? So that does this. Is that okay? So this is a Duped solution. This is Duped assumption. So how do you do that? So you have to observe. Normally you can have two observations, or you can have on it. So you have a well in between. It's a worksheet. Then you have two observation wells. Is that okay? You can have so many of them along. Then as you pump out water, you take the measurement. You take these measurements. How the change in, so that you can determine the change at which the change of what, and the change in the height of the water table as you pump out water. Is that okay? As you pump up water. So when the water flows through, it flows through a surface. Water is flowing through a surface in the well. Water is flowing through a surface. Now for that surface in which water is passing is given by areas. Remember, if you have a cylinder, it is the circular. When what forms, if you pour water into a basin, in fact, it gives you that circular shape. Is that okay? That's a flow in which water flows into that surface. It is a circular surface. So what happens at the water, as the water flows, it flows. Remember, if you have this is the height of the cylinder, and water is flowing along the surface into the surface of the cylinder. Now, for the area in which this water flows through, it is the circumference of the cylinder times this length. When you cut the surface, that's why it is 2 pi. Remember, the circumference of a circle is 2 pi r. 10 times the height will give you the water in which entering into a cylindrical shape. Okay, through its side. Is that okay? And that's how water flows. Remember, that's what water is. Remember this well. That's how water flows. Remember, is that okay? Now for this cylinder, now if you take a small height here, close to this, let us give it a net height h. Okay, and there is a distance here. The R. Is that okay? So now for this is the R here, and this is the H here. This sensor, sorry, and H. Is that okay? So now when the area in which water is flowing through into this area will be given by the area R at 2 pi R H. Flowing into the well. Is that okay? Remember, the well, water is coming, if this is the well, you have that the water is coming through all the sides. Is that okay? Flowing into the well through this area, total area. Is that okay? This will be the total area. 2 pi, the dimension of the well. This is the flowing. So after this water will be flowing in this side, will be flowing for in a circular part, in such a cylindrical part into the well. Now for using that, we say that using Duped assumption from that, remember from that still, he said that Q is equal to V times A. V times A. Well, yeah, A is the area of this area here. Is that okay? And our V is I times K. Q. Is that okay? So now we want to determine. Remember, we have these two observation wells. We have this H. This is the H, which means water is flowing into the surface. Is that okay? And so this here, so the water is flowing into the surface. Here, the water is flowing into the surface. This small surface. Is that okay? So you can integrate. So you make here, and you substitute here. You bring here our. So you solve the you cross multiply. You bring our the R here. So when you integrate, these are small areas. When you integrate to get the total radius in which water is flowing into the different pressures, the high difference will relation with this point, then be able to when you interpolate this, be able to determine you make the Kelly subject. Is that okay? So just interpolate this from H1 to H2. From H1 to H2 causing that flow. Remember this difference here. It's this difference here which causes the flow. This difference here causes what it gives you an hydraulic gradient divided by difference from here up to here. Is that okay? Divided by the difference from here up to here will give you a flow through that material. Is that okay? So when you integrate this, obviously will be in. 1 over R with respect to R is equal to N. Remember our integration engineering mathematics 2 or 1. Then this here, this is a constant. This is H. Remember it is you add here 2. When you integrate with, remember you add. It's the reverse of depreciation. So remember depreciation. So if you add, it becomes a square. But over 2. It will be, when you integrate H, it will be H squared divided by 2. Is that okay? H squared divided, you divide. It is N plus 1 over N plus 1. Is that okay? So when you do that, remember there is a 2 here. This 2 we cancel with this other 2. So remember 2 pi H squared into minus H squared. Is that okay? So when you integrate this, it becomes H squared over 2. But this 2 we cancel with that. So we get with 2 pi K. 2 pi K into H squared minus H1. Now for this one will be H squared minus this H1. We substitute. This will be R squared over R. Remember, because when you integrate in of R, in R, this will be R at over. Now when you subtract in, now for division logarithm, when you subtract 2 logs, it's same as dividing those two numbers. Is that okay? Dividing those 2 numbers. If it was add, it would be multiplication. Is that okay? So you get this. This is for unconfined aquifer. But for confined aquifer, the H in which water is flowing is constant. You don't know the difference between these two here. The H here was a variable of the aquifer in which water flowing into, the direction in which water is flowing into, but here the H is constant. The H is going to be 2 pi K, the H over the R. Where the H over this is the pressure, and the change. This small change will give you the gradient over the small change in R give the pressure gradient, or the hydraulic gradient. Is that okay? This H is constant. And if the H is constant, we do not integrate it. It should be just small h. Okay, now for when you integrate a constant here 1, and there is no variable, and our H was constant, so we put it out. Here is 1 to be just H, be H2 minus H1. This one remains the same the way it is the other side. Is that okay? So you get now for a confined aquifer. So the difference that here, the only difference as you can see here, is a 2. Remember the other 2 disappeared because there was H squared. When you integrate a variable, you get H squared. It is maybe x power n plus 1 over n plus 1. Therefore our n here plus 1 plus 1, it was giving us 2 over 2, the 2 cancels there. But here our 2 remains. Is that okay? Because it's not being cancelled, there is no. This was a constant, there was a small h. Is that okay? And also our h is outside here. Is that clear? So you can pass through these other examples. Is that okay? You can pass through. Now for determining K here, but we have found that the K here, the material is 1 layer. The material is 1 layer. What if? Now for determining for the K for a specific material, homogeneous, isotropic, that all the properties are the same. Is that okay? But if the material is isotropic but different layer, now for the K's are varying. Let us take a case that our K, we have 2 layers. Let's take a case you have material, different materials. Now for them, you have done your laboratory test and found that here, this layer here, it is K1 and it is H1 of thickness H. Here also has a different K, K2, K2, H, H2, and this is K3, H, H3. So now you want to determine the vertical permeability of this material through this layer. Now we want to determine what is the K, overall K, the overall K, or the permeability of this stratified from different stratas. How water is moved through the behavior of water passing through this of such structure made of different layers. Therefore, K vertical will be equal to K vertical will be equal to H1 plus H2 plus H3 divided by K1. So divide by H1. This H1 is divided by K1 plus H2 divided by K2 plus H3 divided by K3. Now for this, we'll give the overall permeability, vertical permeability. But still, for such also there will be an horizontal permeability. So when the water flows, water will be flowing vertically, but also water will be flowing horizontally along with these layers. Is that okay? Now for what will be the horizontal permeability, overall horizontal permeability of this layer? From how can you predict now how water flows through this layer horizontally? This one will be equal to still K1 H1 plus K2 H2 plus K3 H3 divided by H1 plus H2 plus H3. Is that okay? So for K horizontal, for these three layers, the overall permeability horizontal will be this K1, but for the vertical permeability, water moves vertically, or the percolation through the soil vertically, it will be K1 plus H2 plus H3 over K1 over K2 plus H2 over K2 plus H3 over K3. That is because here we have been predicting for a single layer. That layer is homogeneous and isotropic, it's the same. But if you have different layers, if for instance this aquifer is made of different layers, so you determine for each layer, for K for each layer, then you can use these formulas to determine the overall permeability horizontally and vertically, the permeability coefficients. Is that okay? Permeability coefficients. So you can pass through this example of this was a non-confined aquifer or unconfined. Okay, so next time when we meet, we are going to look at